Hello everyone, welcome back to Discrete Mathematics again with me Adila Krishnadi. So now we continue with the notion of degree. We still talk about graph. Earlier we talked about neighborhood of a node, and now we look at the notion of degree. So degree of a node phi, denoted by this notation, degree of phi, deg phi. In the case of undirected graph, is simply the number of edges incident with phi. Number of edges incident with phi, except that each loop at phi contributes twice to the degree of phi. So the number of edges incident at phi and the loops are counted twice. So the loop will be counted here once here and once here, right? Now, if the degree of phi is 0, then we call phi isolated. If degree of phi is 1, then we call phi abandoned. Isolated, abandoned. So now in directed graph, the notion is slightly different because you have directions. In a D graph, you have in degree, so the number of nodes incoming, the number of edges incoming to the node phi. So incoming meaning that the node phi is the target of an edge, so the number of edge going into E. And then out degree of a node phi is the number of edges outgoing from phi. So where, or in other words, the number of edges where the source of those edges is phi. And the degree of a node is simply the sum of the incoming and outgoing, the in degree and the outgoing degree. So let's see some examples. So this is an undirected graph, and we want to determine the degree of each node. So degree of A is, of course, so you count the edge, you have 1, 2, and then 3, and then the loop is counted twice, so therefore 5. Degree of A is 5. 1, 2, 3, and then this is counted twice, so 3 plus 2 is 5. Degree of B is 1, 2, 3, and 4. Degree of C is 1, 2, and 3, so 3. Degree of D is then, well, 1, 2, 3, 4, and then you add 2 for the loop, so therefore it's 6. Yeah, that's the degrees of each node, right? Now so notice one thing here, right? If you sum the degree, you get 18, right? Which is even. Yeah, so keep this in mind. All right, now let's have a look at the undirected directed graph. So here is our example of directed graph, and we want the degree of each node. So degree of A is, well, actually we should say in degree. Let me just erase this a little bit. So there is an outgoing degree of A. This is 1 because of this, and then incoming degree of A, in degree of A is also here 1. Yeah, degree of out degree of B is 2, and incoming degree of B is also 2. Yeah, And now, how about C, the outgoing? Yeah, the outgoing is 1, 2, and 3. The incoming is 1 and 2. So 2. So it is possible here for a node to have different incoming and outgoing degrees. How about D? The outgoing degree of D is 1, and the incoming degree of D is 2. 1 and 2, right? How about E? The outgoing degree is 1 and then 2. The incoming degree of E is, well, 1, 2, and 3. Finally, for F, the outgoing degree of F is 0, and then the incoming degree of F is also 0. Now let's sum this. Can we find something interesting? If we sum this, then if we sum this, we get we have, this is 9, and this is also, sorry, do I make a, oh sorry, the outgoing degree of E should be not 2 but 1, 2, and 3. Here I forgot, so it has to be 3 here. So therefore the sum is actually 10 here, and this is 10 here, so they are the same. Yeah, this is interesting observation, right? We will see whether this holds in general. Now but before that, let's see some exercise. Let's do some exercise again with the same graph: Indonesian provinces in the island of Sumatra, and orbit strings of length 2. So find the that we saw earlier, right? So find the degree of each node in these graphs.